Hello, this is a presentation of image processing techniques for denoising. It is for course number EEE6512 at Image Processing and Computer Vision. To start, this presentation goes through four traditional denoising techniques: the hybrid median filter, Wiener filter, complex diffusion, anisotropic diffusion, and the four state-of-the-art denoising techniques. They are non-local means filter, wavelet denoising, BM3D, which is short for block matching and 3D filtering, and KSVD. All of them are tested across 6 different types of noise. MSE, SNR, PSNR, MAE are calculated for objective signal strength evaluation, and SSRM is also computed to evaluate subjective visual quality. Now, the purpose of this project is to find which denoising techniques perform the best, given certain types of noise. First, as for noise generators, I use MATLAB built-in noise functions to get Gaussian, salt and pepper, Poisson, and speckle noise. The Gaussian has default 0 mean and 0.01 variance. The salt and pepper has default 0.05 noise density. The Poisson is generated from the data instead of adding artificial noise to the data. The speckle has default 0 mean and 0.04 variance. In addition, I have two noises based on MATLAB. The rise noise also depends on the data itself, and it is not addictive. So to add rise noise to the data, what it really means is to make the data rise distributed, while the uniform noise is signal dependent and it has default 10 noise level. Here, let's take a look at what a noisy image looks like. We can see the visual effects of Gaussian and rise noise are similar, the same to salt, pepper, and uniform noise. Poisson noise seems to have the lowest noise amplitude, while speckle noise seems to have the highest noise amplitude. This image both will be used in the traditional denoising technique section. So we can see the same effects on the image here, which will be used in the state-of-the-art denoising technique section. Now we are going to explain a little bit about traditional denoising techniques. First, a basic median filter just returns the median value of 3 by 3 image array. A hybrid median filter returns the median value of the 2 central pixels, which is better in noise reduction and edge preservation. It's clear that hybrid median filter performs better, which has lower MSE and higher SNR and PSNR in all noise types. Second, a Wiener filter does a linear estimation of the original image and executes an optimal trade-off between inverse filtering and the noise smoothing. The image quality evaluation metrics are summarized in the table, which shows it does a good job of reducing rise noise and speckle noise. Third, the linear and the nonlinear complex diffusion are based on the Free-Schrödinger equation. We can see that they have approximately the same denoising ability in all noise types and behave best in rise noise compared with the others. The last one is anisotropic diffusion. It aims at reducing image noise without removing significant parts of the image content. Anisotropic diffusion equation 1 favors high contrast edges over low contrast ones, while equation number 2 favors wide regions over smaller ones. According to MSE, SNR, and PSNR shown in the figure, equation number 1 performs better in Gaussian, Poisson, rise, and speckle noise, while equation number 2 performs better in salt and pepper and uniform noise. In order to quantitatively compare all the results, MAE, mean absolute error of each traditional method, is computed and plotted. These two are for Gaussian and speckle noise. These two are for salt and pepper and uniform noise. The results indicate that MAE of hybrid median filter and Wiener filter are always lower than MAE of complex diffusion and anisotropic diffusion, where the noise amplitude varies from 0.1 to 0.8. Here we are going to explain a little bit about the 4 state-of-the-art denoising techniques. First, a mean filter. Now it is very similar to median filter, except instead of returning the median value, it returns the mean value of the 3 by 3 neighborhood surrounding the corresponding pixel. Non-local means filter takes a mean of all pixels in the image, weighted by how similar these pixels are to the target pixel. This results in much greater post-filtering clarity and less loss of detail in the image. It is clear that non-local means filter performs better, which has lower MSE and higher SNR and PSNR in all noise types. Second, wavelet denoising runs images through a wavelet transform, which provides a multi-resolution representation using a set of analyzing functions. Both hard and soft thresholding wavelet denoising are completed and compared in this project. Also, we use a dual-tree complex wavelet transform, which overcomes some limitations that produces 6 subbands at each scale. We can find that the overall performance of soft thresholding wavelet denoising is better than hard thresholding wavelet denoising, except for rise noise, which only has slight difference in terms of MSE. The third technique is BM3D. It is a novel image denoising strategy based on an enhanced sparse representation in transform domain. By grouping similar 2D image blocks into 3D data groups, the image quality evaluation metrics are summarized in the table, which shows it has state-of-the-art denoising performance on all noise types. We will see this later on. Lastly, we are going to be using KSVD, which is a dictionary learning algorithm for creating a dictionary for sparse representations via a singular value decomposition approach. Using the KSVD algorithm, we will get a dictionary that describes the image content effectively. 3 training options are considered: an over-complete discrete cosine transform dictionary, a corpus of high-quality image database with globally trained dictionary, and an adaptively trained dictionary. These 3 different dictionaries have nearly identical overall performance since CSNR and PSNR tend to overlap. However, based on MSE, we can still tell that adaptively trained dictionary behaves best among 3. Again, MAE of each state-of-the-art method is computed and plotted in order to quantitatively compare all the results. These 2 are for Gaussian and speckle noise. We can see, unlike traditional denoising techniques, they have very close performance. These 2 are for salt and pepper and uniform noise. The results indicate that MAE of BM3D and the KSVD are always lower than MAE of non-local means filter and wavelet denoising in the whole noise amplitude scale. This seems to meet our expectations because BM3D and the KSVD have the most complex algorithm and take the most steps to reduce noise in the image, which requires lots of time for computation as well. Here, we calculate the Structural Similarity Index SSIN, which is more related to human perception. The top 4 denoising techniques are listed for each noise type. To start, we are looking at Gaussian noise. In the Gaussian noise, KSVD and BM3D get rid of most noise, so slight details are lost. The next one is salt and pepper noise. In salt and pepper noise, hybrid median filter does a pretty good job, as we can hardly find a difference compared with the original image. So with the Poisson noise, BM3D and the non-local median filter performs best, but still have a little blur. For rise noise, again, KSVD and BM3D get rid of most noise, making the image cleaner than the others, though some details are not preserved very well. This is for uniform noise, which is very similar to salt and pepper noise, and the results are also the same. The image runs through hybrid median filter looks almost exactly like the original image. Okay, moving on to the last one, speckle noise. This time, anisotropical diffusion equation number 2 does the best, which preserves the majority of the details. However, we can still find a lot of noise on the image. Now, I will give a quick demonstration of my program. As you can see, just very basically, with the image here and this for the noise generators. And here apply the traditional denoising techniques. Basic median filters compared with hybrid median filters, and the Wiener filters, linear and nonlinear complex diffusion, anisotropic diffusion equation number 1 and number 2. Then use state-of-the-art denoising techniques. Basic mean filter compared with non-local mean filter, and the soft and hard wavelet denoising. Then BM3D, and the last one, 3 training options in KSVD. Finally, I compute MSE, SNR, PSNR, and MAE, also the SSIM for each image. Separate functions are widely used in this program. I have shown all the results in the PPT as you have seen. Okay, in summary, hybrid median filter is effective in removing salt and pepper noise and uniform noise. Anisotropic diffusion equation number 2 favors speckle noise. Non-local mean filter is best at reducing Poisson noise. BM3D and KSVD are the two most powerful denoising techniques that achieve leading denoising performance. Detailed data reveal that KSVD outperforms BM3D a little in high noise situation with all the noise levels above 0.5. However, it usually takes BM3D a few minutes to complete the computation, while it often takes KSVD a couple of hours to do so. Most of the time are spent on creating the dictionary, which is really time consuming. So I think BM3D is the best one that has the optimum trade-off between performance and efficiency. That's pretty much everything. Thank you for your time.